Good evening. So today we are going to discuss about resistive transducers. So resistive transducers are those whose transducers in which the resistance is changes due to the change in some physical phenomena. So here we know the formula R equal to rho L by A, where rho is the resistivity and L is the length of the conductor and A is the area of cross section. So the resistivity depends upon the type of material, which type of material we are selecting. Based on the type of material, its resistivity will change. Length is a physical parameter and A is a cross section area. So these two are the physical parameters and this is the material property. So by changing these three quantities, we can change the value of resistance, right? So we know the formula. That's what we explained. R equal to rho L by A. R in terms of ohms, L in terms of meters, A is meter square, and resistivity of the conductor is ohm meter. So by changing R, so in order to change the R value, L, A, and rho value are going to be changed. Excuse me. Right. Now there are different types of resistive transducers are there. So potentiometers, then resistive pressure transducer, resistive position transducers, strain gauge, thermistor, and resistance thermometers. So these are the various types of resistive transducers. We'll go in detail about these different types of resistive transducers. Now potentiometer. Simply we can say how the value of resistance is going to be changed based on the change in length. So as we know, R equal to rho L by A. So here L is going to change. So from A point to B point, let us say this is A, B resistance is in terms of some X ohms. Okay. Now we are making a point C terminal where it is a sliding wire. We can move in either the direction. So depending upon the position, for example, if you are connecting at this point, so up to here, this is the resistance is going to be comes uh, into the circuit. So now this is the place where VC is connected, nothing but the place where we are going to get the terminal. So the total voltage across A and B is Vs, nothing but supply voltage or source voltage. And the point C, wherever you are going to connect, that is going to be at the point C. So the voltage from A to C becomes Vc. Okay, similarly, if we change the position C to here, so Vc value, nothing but AC, VAC value is going to be gets changed. So it is changed because of the change in the resistance value. Okay, so there is a sliding contact which we can move. Simply we can wait. Right. Now a potentiometer where we can have either in terms of linear in nature or rotational in nature. So earlier the diagram what we have seen is linear. So in that case we are going to move the sliding wire contact either horizontal only. So either this direction or this direction. But whereas in case of potentiometer in this diagram where we can have a rotational. Okay. So we can have a sliding wiper where it is going to be rotate. So these are the three terminals. So simply in your laboratory, in the machines laboratory, you might have seen rheostat. So rheostat is having three terminals, fixed terminals, two, and one variable terminal. This is the variable terminal. So whenever you are moving through the sliding contact, then the value of resistance is going to be gets changed. Nothing but as the length is going to be gets changed. That is linear in motion. But whereas in case of rotational potentiometer, so we are going to move this in terms of a rotational, nothing but angular, circular. Okay, so you can observe this the second diagram. An animation is there. Terminal A, B, and C are there. So between A and B, sorry, if you are connecting the terminal between A and C, the resistance is fixed. If you connect between A and B, the B position is going to be gets contacted with different places. Okay, the best example is In the laboratory, you are using a potentiometers. So whenever you are changing the value of voltage in RPS, so the potentiometer, which is we are rotating in a circular direction or circular manner. So in a similar way, we can change the resistance. If the resistance is changes, automatically the voltage will change and current will change accordingly, right? So we can have a linear motion or we can have a rotational motion. Okay, we can also call it helix form. So helical form, nothing but just like a spring. Okay, or also called as helipods. So potentiometer, if it is in linear, we can call it a linear potentiometer. If it is a rotation, we can call it as a helipod. Right? Now coming to the another one, resistance pressure transducer, where we are going to apply the pressure. Okay, as we have seen, these are the bellows. Okay, in the previous classes we have said what is bellows. So whenever you are applying a pressure, so it is going to get compressed. Okay, so a spring is going to be gets connected, and here these are the things what we can have, the winding. So we can have the winding. So in that winding, so here there is a contact terminal will be there. So the contact terminal will get in contact with that, so that as the contact terminal positions are changing, the resistance is going to be get changed. So here pressure is going to applied as an input. Here pressure is going to applied as an input, and that pressure is going to be converted as change in resistance. So resistance leads are connected to the bridge circuit, so that here from the this terminal we can change the resistance value. This is another type of structure. Here also we are going to apply certain amount of pressure. There is a spring is connected, and this is a diaphragm. Okay, so just like a air piston, so whenever it is applied through the force or through the pressure, so the spring will get compressed, and then the contact terminals are going to be gets changed, so that the amount of resistance is going to be changed. So this is the resistance value. Okay, between this terminal and this terminal we can have certain fixed resistance, and if you get contact at another terminal, then so as length changes, L changes, then automatically the amount of resistance value changes, right? So the same explanation what I have given in this one. And this is the resistance position transducer, which is also similar. Okay, so here this is the winding, not the rheostat what we have observed in the laboratory, which deals with this resistance position transducer. So here the position is going to be gets changed. Okay, so the position is going to be gets altered with the conducting strip. So the conducting strip will be there. There is a wiper will be there. Wiper can be moved in either the direction. So horizontally we can move. Okay, so as this is the contact terminals. Okay, these are the contact terminals. A and B is the length of the total wire, and if you are go on moving this shaft in either the direction, the contact position will change. So as the contact position will change, then automatically the amount of resistance will change accordingly. So we can see the animation at the right side diagram. Okay, so here the path is from 0 to 300 mm. Okay, 0 to 300 mm of distance. So as the resistance from 0 to 12 kilo ohms, let us say. So as it is gone moving in either the direction, okay, according to the length, amount of resistance will change, because we know that R equal to rho L by A. So if L changes, the amount of resistance will change. So L is going to be changed through the position of the contact terminal, right? Now the same, a sliding wire transducer. So here we are using a slider, so which can be moved in either direction, so that according to the position, so total R1 plus R2 becomes total capital R. Okay, R equal to capital R1 plus R2. When the sliding contact position is going to change either in the upward direction or in the downward direction, then automatically R1, R2 values will change. R equal to R1 plus R2. So always this condition will get satisfied. R equal to R1 plus R2. But whereas individually we can have R1 and R2 values will change according to the position of the sliding contact. Okay, so the same we can observe in terms of voltage also. So we can observe in terms of resistance, or also we can observe in terms of voltage. So as the bottom terminal deals with the 0 voltage, okay, and the positive terminal deals with the plus 50 volts. Okay, so whenever you are go on moving towards the top one, then automatically the amount of maximum voltage can be obtained and it can be displayed on the voltmeter or else multimeter, right? And strain gauge. Okay, strain gauge, the experiment what we have done in the laboratory, which is same. So whenever you are applying certain amount of strain on the strain gauge, okay, nothing but there is a change in physical dimensions. There is a change in physical dimensions. As the physical dimension changes, automatically on the strain gauge, nothing but here also resistance value. The nothing but the strain gauge gets influenced with the strain, then automatically there is a change in dimensions of length as well as cross sectional area. So whenever it is gets compressed, automatically length will be reduced and cross sectional area will be increased accordingly. So whenever these parameters are going to be gets changed, then obviously it is going to influence the value of change in resistance value. Okay, then so we can observe there is a sliding, a cantilever is there. We can observe there is a cantilever. On the top of the cantilever, there are R1, R3, and the bottom of the cantilever, there are R2 and R4 are there. Okay, green color line and red color line like that. Okay, so whenever certain amount of force is applied in this positive direction, okay, just you can observe the various parameters parallelly. So the length is going to be gets increased, as well as here we can observe the value of resistances, R1 value, R2 value, R3 value, R4 value. So on the cantilever, the strain gauges are placed whenever you are applying certain amount of force. Here you can observe this is the fixed end. Okay, this is the movable end. So simply it is bending. It is bending. Whenever it is going to bend, automatically the amount of there is a physical changes, nothing but certain strain is going to be applied on the strain gauge elements. Then automatically the value of resistance are going to be gets changed because of change in their dimensions. You can observe whenever the force is applied, the lengths are changing in the strain gauge. So in order to increase the length, you can have this kind of shape. Okay, so these two terminals are connected here, and there is a device where we can apply certain amount of force and how much amount of pressure can be applied, so that how much amount of distance has taken, that also will be taken into consideration. And we have applied these parameters to the bridge. So it's a 4-arm bridge. So it is a 4-arm bridge. So in a 4-arm bridge, we are going to whenever it is going to be get strained, then automatically the value of resistance are going to be changed. Right. Okay. So this is one type of, a strain gauge where we can measure the strain in terms of voltage or in terms of uh, resistance also we can measure. So here this is the terminal where we can measure the voltage. So in the laboratory also we can have a strain gauge experiment. There we can observe how much amount of pressure versus voltage and pressure versus resistance. Both the things we have drawn the waveforms, right, or graphs. So it's just like an elastic body. Okay, just like it taken a rubber band. If you start applying the force on the opposite direction, then it will be enlarged. So automatically the cross-sectional area of the rubber band will come reduced. Okay, as well as the length will gets increased. Whenever it is gets compressed, then its area of cross-section will gets increased and length will decrease. The same principle we are going to operate, or we are going to use in the strain gauge. So these strain gauges are placed at the 4 arms of the bridge. Okay, 4 of the arms of the bridge are replaced with the strain gauges, so that whenever we are applying certain amount of strain on the strain gauge, okay, then automatically the amount of resistance will change, which is going to be influence the value of voltages. Okay, so these are the terminals what we can have. The electrical wires, leads are there, where we can have the strain gauges as of in terms of a huge in length. Okay, the strain direction, whenever you are applying certain amount of force, so their length will increase or decrease. Okay, so the strain direction will be either horizontal we can increase or decrease. So we can have the practical strain gauge diagram. So what is the size of the strain gauge? We can call it as a grid width. So grid width means what is the effective value of the resistances, right? Grid length. Total base strength. Base is nothing but the entire structure where we are placing the strain gauge. Okay, grid means the exclusively the term strain gauge which has been placed on the base. Okay, it can be soldered. Okay, soldering can be takes place so that we can have the terminals and wherever we want to can connect to the required space. So we can have a derivation for the calculation of gauge factor. Okay, it is denoted with either K or S. So which is can be defined as it is also called as sensitivity of the strain gauge. So delta R by R divided by delta L by L. So change in resistance by ratio of change in resistance to resistance and change in length to length. So these parameters are going to be changed. So R equal to rho L by A. So where rho is the resistivity of the material. So for the strain gauge, the material has been fixed so that nothing but the selected for the selected strain gauge, the material has been fixed. So resistivity won't change. So R is proportional to L by A. So where resistivity is a common term, nothing but a constant. So R is proportional to L by A. So where L deals with the length and A deals with the cross sectional area. So here the strain gauge we are going to calculate the strain value or strain gauge factor value. Either we can be denoted as S or K, that is delta R by R divided by delta L by L. Okay, so the gauge factor or gauge sensitivity we can call it as, right? So length, change in length, there is a derivation. So if this is the resistance value, okay, of a strain gauge having certain length L, okay, and it is having certain diameter capital small d. So whenever it has been applied certain amount of force so that the length will be increased to L plus delta L, as well as the d value is going to be gets changed. So that the value of R resistance is going to be changed as R plus delta R. So from this formula, rho equal to, we can have the strain formula. Strain equal to, strain can be represented as delta, that can be delta L by L by L. So this is the value what we can have. And so that from the formula K or S or K equal to delta R by R divided by sigma or delta L by L. So the change in resistance with respect to resistance and change in length with respect to length. So these are the factors what we are going to calculate. So where delta is called as a strain in the lateral direction, means the horizontal one, right? So how these values, whenever you are applying certain amount of force, how the radius will change. So radius is nothing but diameter by 2, d by 2, or equal to d by 2, or square, d square by 4, because it is a conductor size. So we can have certain resistance value rho into L by pi d square by 4. So from that expression, we are going to calculate how the value of length is going to be gets changed as the length increases to L to delta L, L plus delta L, and resistance value is going to be changed to R plus delta R value. By that time, how the value of D is going to be gets changed. So that can be calculated. So rho is the specific resistance of the conductor, which will be fixed. L is the length, D is the diameter of the conductor. So this is the entire derivation which we can substitute mathematically. So R equal to rho L by A. So where R is the resistance, rho into L. L becomes L plus delta L. A cross sectional area of the conductor. So initially L by A is the factor. Now what is L? What is A? L is nothing but L plus delta L, and A is nothing but pi by 4 into D minus delta D square. Because as the length increases, the diameter will decrease. So that D minus delta D. So that will be the factor. So we can have expanding of these statement, this expression, as well as neglecting the higher grade squared terms. So that finally, at the end of the derivation, we can have the micro strain. So in the axial direction, that is delta D by delta L by L. And from that, we can calculate this is the entire by rationalization. So simply mathematical derivation we can apply so that we can obtain the value, and finally the value of gauge factor can be derived as like this. So R equal to K or S equal to 1 plus 2 mu. Okay, so that is the value of strain gauge or gauge factor, right? Now coming to the thermistor. Thermistor stands for thermal resistor. Thermal resistor. So thermistor. So it means that temperature versus resistor. Okay. So we can have two types of materials. Temperature is proportional to resistance. So nothing but if temperature increases, resistance increases. If temperature decreases, resistance decreases. So we can call this type of material as positive temperature coefficient. Nothing but PTC. And there is another type of material. If temperature increases, resistance decreases. Nothing but these are inversely proportional. Nothing but T is inversely proportional to R. Nothing but T is proportional to 1 by R. If T increases, R decreases. Like that. Okay, these kind of materials we can call it as negative temperature coefficient material. So where the thermistor comes under negative temperature coefficient. So if temperature increases, temperature is on the x-axis and resistance on the y-axis. Temperature increases, resistance will decrease. It's a non-linear curve. So in the laboratory, we might have done the experiment. So the thermistor can be represented as this is the symbol. So where this represents with the international standard. So the resistor value, normally resistor we can represent as like this, but thermistor can be represented as a line of like this, right? Or this is the one. So nothing but it is going to be varied. Okay, these are the what you can say temperature versus resistance characteristics, right? So these are the practical available thermistors. So bed type thermistors, probe type, washer type, disc type, screw type. So like that, there are different types of thermistors are available in the market. So normally మనం probe type thermistors lab lo use చేస్తాం. Okay, right. So there are the classification beds, rods, discs, etc. So depending upon the type of, the range of temperature, these values are going to be get changed. Okay. In some cases, the resistance of thermistor at room temperature may decreases much 6% for 1 degree centigrade of rise. So if 1 degree centigrade temperature increases, 6% of the resistance is going to be decreased. So 1 degree centigrade increases means around 6% of resistance, okay, will decrease. So that is the proportionality what we can have. So the available types of thermistors in the market. Advantages: small in size, low cost, fast response over narrow temperature range. Even at the short temperature ranges also we can have a fast response in the change in resistances, and good sensitivity in negative temperature coefficient region. So of course the thermistors works under negative temperature coefficient region. And cold junction compensation. Cold junction compensation is not required due to the dependence of resistance on absolute temperature. So about the value of absolute value of temperature, it depends upon this one. So here the terminals are there, okay, where we can have cold junction and hot junction. The hot junction is the place where it is going to be gets heated up, and the cold junction where it is going to be left free. That terminals are going to be connected to the processing blocks. Okay, so contact and lead resistance problems are not encountered due to the lost resistance. Of course, this is also one of the as compared with the because we can have the diagram. So here we can observe there are different types of thermistors are there. So with respect to these resistance value, the lead resistance values are very less. So we need to neglect the lead resistance values. And the limitations, the characteristics are non-linear with respect to temperature. Okay, that is one thing. For unsuitable for wide temperature changes. So from minimum to maximum, there is certain restrictions are there. So here there is a kind of restrictions is there, so that we cannot operate this for the wide ranges of temperature. At very low excitation currents to avoid self-heating. So in order to avoid the self-heating means whenever it is going to be gets heated up, the amount of resistance is going to be reduced. So in order to avoid this self-heating, so low excitation currents can be provided to maintain the temperature constants. And need of shielded power lines, filters, etc. due to high resistances. So in order to avoid the what you can say the changes of the resistances value, then we can have the shieldings also. And resistance thermometer, nothing but RTD. Resistance thermometer, RTD. So here these characteristics are linear. Okay, increasing characteristics. So with respect to temperature and the value of resistance. So as temperature increases, resistance increases. Nothing but positive temperature coefficient type of materials, right? So this is the one. Resistance thermometer, or also we can call it as resistance temperature detector or TD. So where this portion we can place in the water or nothing but in the hot water which has taken in the beaker, and yes, the terminals are there which can be connected to the signal processing blocks to observe the amount of temperatures, right? Okay, so this can be connected as a form of bridge. So all the four terminals can be replaced with the resistors or nothing but resistance thermometers, where these are going to be gets affected by the temperature value, so that according to the variation of the temperature, the amount of resistance will change. So three resistors R1, R2, R3. So these three are fixed resistors. Then these resistors are going to be changed based on the amount of temperature, so that the amount of the bridge can be balanced accordingly. So the leads, how it has to be connected, where is the insulating materials, and these things are there. Now coming to the inductive transducer, so where we can have some variation of self-inductance and variation of mutual inductance. These are the two things what we can have. So variation of self-inductance can be processed through this formula, where phi equal to Ni by R. So where N is the number of turns and R is the resistance and I is the amount of current flowing through. So the flux, okay, and the rate of change of flux linkages, d phi by dt, nothing but N by R, nothing but these two are the constant, where N is the number of turns and R is the reluctance value, and di by dt, where the current is the only the terminal which is variable. So if you are saying in terms of inductance value, so L equal to 1 by R, nothing but reluctance. Not this R stands for reluctance, not resistance, right? So strictly speaking, we can write reluctance as like this. Nothing but two lines R. Okay, so this we can call it as the reluctance, right? Which is equal to 1 by L. So reluctance and inductance are the inverse proportional elements, right? So E equal to N d phi by dt. So if you want to calculate in terms of voltage, N into d phi by dt, where N is the number of turns and phi is the flux. So d phi by dt means rate of change of flux linkages. So electromagnetic induction formula. So self-inductance value we can calculate L equal to E by di by dt. E by di by dt. So if you substitute that values, so that we can get N square by R, where N is the number of turns, R is the reluctance value. So here these are the terms what we can have, the reluctance value L by mu A, right? So from the equation we can observe that the self-inductance value can be changed based on the changing number of turns, based on the geometric configuration, and based on the permeability of the magnetic circuit. So nothing but, so N, if you change N, the value of L change. So in order to change the value of N, N will be changed, geometrical configuration, nothing but the length, so that whether you are going to place in the what you can say linear, or it can be a circular like that. Okay, the permeability is mu. Okay, so N, L, mu, these are the factors which are going to be altered, so that the amount of value of L will change, so that the self-inductance is going to be gets altered. See, just observe here. So here we can have the output terminal. So these two terminals, the top and the bottom terminals are the fixed terminals, where we can observe the total inductance value. So if you move the contact or the sliding terminal in the vertical direction, I think, but displacement is going to happen in the vertical direction, so that the amount of number of turns are going to be gets changed, so that the amount of inductance are going to be gets changed. So N is going to be changed. number of turns. So changing with this number of turns. So this is a circular. Okay. So angular inductive transducer, we can call it as a angular inductive transducer. And the first diagram is called as a linear inductive transducer. Now changing the permeability. So permeability can be changed based on the core. So what type of magnetic material we are going to use, on which core the windings are wounded, and what kind of materials we are using. So that and all can be depends. Okay. So the iron core is surrounded by the winding. The iron core inside the winding is going to be its permeability can be increased, so that the amount of inductance also going to be increased. So mu is proportional to value of L. And variable reluctance. If you change the reluctance value, the amount of inductance also will change. So as we have gone through this diagram even in the previous case, so there is a winding. So that winding are framed on the or wounded on the metallic former, and there is another metallic former will be there. So in order to move the flux, so there should be certain air gap. If you change this air gap, automatically then the amount of reluctance will change. If air gap increases, the reluctance increases. As reluctance increases, inductance will decrease. So your displacement will be taken place in the vertical direction, right? So where n equal to n square by reluctance value, from that we can calculate these things. So these are all the same thing. Depending upon the type of material, we can calculate. So this is the experimental diagram where we can measure the value of reluctance value, so that as the reluctance changes, the amount of inductance will change. So here this is the pivot. Here we can move just like a seesaw motion. Okay. Earlier I said if this is the fixed point, we can move either the direction. So if it is moving like this, it will be as of like this. Okay. If you are moving in opposite direction, yes, it will be off like this. So based on that, the amount of air gap will change. As the air gap changes, the amount of reluctance will change. Okay. This is another method to change the value of reluctance. So mutual inductance. So two coils are going to be placed. So between the two coils, we are going to get the mutual inductance value. So coil 1, coil 2. Okay. So here we can observe there are two coils are there, L1, L2. Two inductance windings are there, because we are going to tap at certain distances. Okay. So from the from the wiper or nothing but from the slider, wherever we are having the position, it is going to be split into two inductance value. The total inductance L equal to L1 plus L2, whether it may be either linear or it may be either angular. Okay. So total L value becomes L1 plus L2. So depending upon the wiper position, it is going to be gets changed. So this is another kind of structure where we can have two different coils are there. L1 coil, L2 coils are there. So here also air gaps will be there. As the air gap will changes, the amount of reluctance will change. Okay. So that we can move this iron. We can move this iron in either the direction. So that if it is moving towards the top side, then automatically this reluctance will change, and according to this reluctance also will change. One is in increasing mode, one is in decreasing mode, like that. Now coming to the LVDT, this is one of the very good application of inductive transducer. So it is also a transformer having a primary winding, one primary winding wound on the central part of the metallic former, and two identical secondary windings. Identical means equal number of turns, right? So the secondary windings are having equal number of turns. So, and they are wounded on two ends of the former, and they are connected in series opposition. So if the two windings, okay, let us say this is winding 1, this is winding 2. If these two terminals are connected, we can call it as a series, right? If the same windings are connected as like this, okay. So here this is the terminal 1 and this is terminal 2. Okay. Between these two terminals, we are going to connect whatever the requirement. But now what we are using, this is terminal 1, and now we are going to connect here like this. and this will become terminal 2. So this is terminal 1, terminal 2. So here the current will enter, okay, and it will move in this direction, and here from here the current will enter. You know about dot rule. Circuit theory like dot rule. So the current entering point can be represented through the dot. So here in the first case, this is the dot and this is the dot. So that these two are connected in series. And in the second case, these two are connected in series opposition. Okay. Now observe this. This is the diagram, LVDT diagram. So this is the metallic former, nothing but a core. We can call it as a core. So the total winding will be there. The primary winding where we can apply the input voltage here, and the two secondary winding, and this is also secondary winding. So secondary 1 and secondary 2 like that. Okay, right. Okay, or else we can go for this is secondary 2 and this is secondary 1. So here also like that represented. So secondary 1, secondary 2. So the two windings are placed like this. Now we can have a core. The core can be moved in either the direction. Nothing but once it will move towards the secondary coil. Once it will, sometimes it will move towards the primary, secondary 1 coil. Secondary 1, secondary 2 will be there, right? We can see the animation. Already we have gone through this animation in the previous class. Okay. Right. So whenever the core is moving towards the right, okay. So this is, let us say this is 1. Green is 1, I think. Yeah. Blue is 2. So if the core is moving towards the green, then the green voltage, nothing but this is secondary 1 voltage, output voltage. This is primary voltage VP, voltage at primary, voltage at secondary 1, voltage at secondary 2, VS1 minus VS2. Nothing but these two are connected in series opposition. Na? So yes, VS1 minus VS2 or VS2 minus VS1 depending upon the magnitude. So as the core moves towards the left direction, the green color waveform is going to be gets increased. Meanwhile, it will be decreased. VS2, nothing but the core is linked with the entire coil of 1. So secondary winding free out. As the secondary winding gets free, the amount of induced EMF in the secondary 2 will be minimum or 0. Okay, so effective number of turns should be linked with the core. So as more number of turns are linked with the core, more amount of voltage can be obtained. As less number of turns are linked with the core, less amount of voltage will be applied. So depending upon the position of the core, the amount of voltage will change. If it moves to the leftward, nothing but secondary 1 voltage will increase. Meanwhile, secondary 2 will decrease. If it moves in the opposite direction, so secondary 2 voltage will increase and secondary 1 voltage will decrease. And secondary 1 and secondary voltage are in series opposition. That's why the two voltage waveforms are 180 degrees opposing together. And the last waveform in the pink color is the difference between these two, right? The same thing what I have explained is there in this one. So we can have the advantage. The linearity is about up to 5 mm. It will be of linear in nature and high output range. Even with the less amplification is required, and it's having high sensitivity. Even for 1 mm of displacement, we can obtain around 300 millivolts of output voltage at the core, and it is withstand with the shocks and mechanical vibrations also, and less friction. So no sliding contact, hence the friction is less. So simply we are just moving the core position. So as the minimum contact portions are there, so that less amount of friction will be there. And low hysteresis. So nothing but the characteristics, whenever the voltage are increasing, nothing but the voltage or the parameters which are increasing in nature as well as decreasing in nature are same in position. Low power consumption, small in size, simple operation, light in weight, stable operation, easy to align, easy to maintain. So these are the various advantages what we can have for the LVDT. And coming to the disadvantages, so large displacement is required for appreciable differential output. I want this much amount of output voltage, so you need to apply more amount of displacement. That is one drawback. So sensitive to magnetic field, because it is a transformer where the flux is going to be produced in the coils or in the core. right? If you place near to any other magnetic field, it is going to be, the flux is going to be get disturbed or distorted, so that the amount of output voltage is going to be changed. And dynamic response is limited by the mass of the core, nothing but as the core is having more weight, so more amount of pressure or more amount of force is required to move. And temperature also affects the transducer because of the coil and its parameters. And there are various applications what we can have for the LVDT. So water tank level measurements, then sheet thickness measurements, then uh, loading springs can be used, and making certain different shapes of the cone shaped curves like that. So just observe this water tank. So definitely the water is going to be filled in the water tank. So once, depending upon the water weight, let us say if the water is fully filled with the tank, 100% of water is there. Let us say this is the weight. If the water tank water is at 50%, what about the weight of the water and tank? And if it is lesser than that, then what about the weight? If it is less than that, what about the weight? So that if we are placing at the bottom these LVDTs, so as the pressure is going to be applied on that one, that pressure is going to be converted into displacement. The displacement causes the change in output voltages, where it can be absorbed in the LVDT. And sheet thickness in the steel industries, the steel is going to be gets manufactured, okay, then it is going to be gets made in terms of rolls, nothing but sheets. In order to maintain the equal thickness of the sheet, we are going to place the LVDT on the top and bottom of the portions. So as the thickness gets increased, automatically the terminals are going to be gets changed, then the amount of voltage will change. According to that, if we are going to apply certain amount of force. Simple example. So చెరుకు రసం తీసే మిషన్ ఉంటుంది. సో చెరుకు దాంట్లో ప్లేస్ చేసినప్పుడు, సో యాజ్ ఇట్ ఈస్ హ్యావింగ్ లెస్సర్ సైజ్, ఈజీలీ ఇట్ విల్ మూవ్. సో అలా యూస్ చేసుకుంటూ పోయిన తర్వాత హీ విల్ ఫోల్డ్ అండ్ అగైన్ హీ విల్ ప్లేస్. What will happen? You need to apply more amount of pressure or not, or else you need to adjust the distance between the two rollers. Okay, the two rollers are connected to the two ends of the LVDT, so that equal thickness of the metal or material can be maintained. And this is another example where we can have, there is a different shape is there. In order to maintain this proper shape of the structure, we are going to place L number of LVDTs at another sides. So each LVDT is having certain parameters. Based on the prescribed values, we can have the correct proper shape of the LVDT, right? And capacitive transducer, here we can have capacitance C equal to epsilon A by D. Already we have gone through about this, where A is the cross section area and D is the distance and epsilon is the permittivity. We can change these things. So by increasing the length or distance, area of cross section, these are all the things all we have discussed in the previous classes. So with the help of a capacitive transducer, we can measure force, okay. And there is another type of construction is there, where we can have, this is, we can measure pressure also from the capacitive transducer. Just observe, this is the diagram. So there are two plates will be there. There are two plates will be there. One plate is fixed and another plate is movable. Okay, so in the previous case we have discussed about whether we can increase, okay, epsilon A by D. We can increase the area of cross section, or we can change the area of cross section. We can change the distance between the two parallel plates. We can change the permeability of the material, dielectric material things, as well as we can apply certain amount of pressure at one side of the plate, so that the plate will bend like this. Okay, there is a plate will be there. Whenever you are applying certain amount of force at one side, it will bend like this. So here we can observe the distance between the two plates will be changed accordingly. Here the distance is more and here the distance is less. Again the distance is more. So as the distance changes, automatically the amount of capacitance will change, so that we can measure even pressure also. So pressure also can be measured through this kind of capacitive transducer, right? So advantages of capacitive transducer: small, useful in small systems, high sensitive, good frequency response. So there is no effect with the stray magnetic fields. And there are certain disadvantages are there. So proper insulation is required between the metallic parts of the transducer, and stray capacitance affect the performance and non-linear behavior. So capacitor also will have a non-linear behavior. And coming to the thermocouples are nothing but the two dissimilar materials. Two dissimilar materials are connected or joined at one terminal, one end, and the two ends are left open. Okay, if you start heating at this junction, okay, we can call this is junction where the two elements are coupled. So we can call this is the hot junction. We can call this the hot junction. If you increase the temperature, automatically there is a voltage will be built up between. There is a voltage will be developed between the free terminals. We can call this is the cold junction. Okay, the same we can have with the help of this, right? Right. So hot junction and cold junction. So here we can have the two metals, chromel and alumel. These are the two dissimilar materials are going to be connected at one end, and the two different ends are connected to the reference junction, where we can have another connectivity through copper wires. Okay, so here we are going to get the voltage. That voltage will be collected through the normal copper wires. Okay, there are different kind of material junctions are there. Just we can see. Okay, so multiple junctions, series of thermocouples, series of thermocouples, series of thermocouples. Nothing but first terminal. Okay, just observe here. Iron, constantin are connected. Then again, iron, constantin, like that. Okay, so series of connections are made. So series of connections are going to be called as thermopile. Thermopile. So thermopile is nothing but series of thermocouples. So copper is connected with the iron. Again, copper connect with iron, copper connect with iron, copper connect with iron, copper, nothing but material 1, then again material 2, material 1, like that, this series. So observe here, these are the lines, nothing but these are the wires are joined at different ends. Okay, so series of different wires, so it's called thermopile. So these are the characteristics of thermocouples. Chromel and constantin is having certain kind of characteristics. Iron, constantin, copper, constantin, chromel, alumel, nicrosyl and nisyl, platinum, rhodium and platinum combination alloys, platinum and rhodium, platinum. So like that, we can have several combinations and their characteristics of like that. Right. These are also comes under positive temperature coefficient characteristics. So there are different types of thermocouples are there. Type E type, J type, K type, N type, T type, U type. So their different temperature ranges are there. So just observe this. E type thermocouples are going to be made as minus 200 degrees centigrade to 900 degrees centigrade temperature ranges we can use. J type, in our laboratory we can have a J type thermocouple is there. So 0 to 750 temperature. So in this range it is going to be gets operated. So here iron and constantin are the materials. Nickel and chromium in the earlier case. Nickel, chromium and nickel, aluminum. Nicrosyl and nisyl. Copper, constantin. Copper, nickel. So like that. So based on the various types of materials, what we are going to couple. Okay, thermocouple. Couple means two. These two are joined at one end called hot junction. These two are left free, open. Nothing but cold junction. If you heat at the hot junction, at the end of the cold junction, we can get the voltage simply. So photoelectric transducer. So photoemissive, photoconductive, photovoltaic. These are the three different types of photo transducers. Okay, so photoemissive. So whenever the photo rays falling on the photoemissive elements, the cathode causes the electrons to be emitted from its surface. So it is going to emit the electrons. Okay, and photoconductive. In the photoconductive, whenever the photo light or light energy is falling on the surface, then it is going to change its resistance so that the amount of conductivity will changes. So resistance and conductance are inversely proportional together. So as the resistance decreases, the conductivity will get increased. And photovoltaic. So as the photo energy is falls on the photovoltaic panel or the photovoltaic cell, it is going to produce the voltage. So emissive, conductive, voltaic. There are three different types of photo transducers. Okay, whenever the radiation falls on the photo emissive devices, it produces the cathodes. Sorry, the cathode produces the electrons. And photoconductive, it is going to change its resistance. Photovoltaic, it produces the voltage. So it is also a photo multiplier tube where we are going to pass the photo ray. So here the focusing electrode will be there, which is going to be entered into this one. And whenever it is falling on this, just like these are the anodes, what we can have. Okay, anode 1, anode 2, like this. So anodes are going to be collecting the electrons. Anodes are going to be collecting the electrons. So whenever the electrons are passing here, so these kept at a minimum voltage position compared to here, voltage will be increased. Again, voltage will be increased. Voltage will increase. So with respect to the first anode to the last anode, so 1, 2, 3, 4, 5, 6, 7, 8th anode. So V1 voltage. Sorry, V1 nothing but at this position. What about the voltage? At this position, what about the voltage? Let us say at the terminal V8. So V8 is far greater than V1, so that we can have higher voltage. As the high voltage is there, more amount of attraction of the electrons will be taken place. So as these are placed as just like a what you can say, a lens of like that, so that multiple electrons are going to be get produced from the we can call these terms are diodes. Okay, so that more amount of electrons are going to be gets increased. So with this increasing of electrons, that's why the photo energy is going to be gets multiplied. So that's why we can call this as a photo multiplier tube. Okay, we can have a fixed supply will be there. We can connect various the resistors. As the resistance or changes accordingly, the voltage are going to be gets dropped. Nothing but all these diodes are placed at different potentials. So there are 1, 2, 3, 4, 5, 6, 7, 8 diodes are there. Individually, we can call these are anodes. Okay, so these photo rays are going to be gets attracted towards the anode, right? So as it is going to be gets voltage is going to be gets changes, more attraction power will be increased. So we can observe a small example. So the attraction of the what you can say magnet. A small magnet will attract small in size. A huge magnet will attract huge in size. Okay, their attraction forces, the flux produced from the magnet also will gets increased. So here all the same principle will be taken place. And the photoconductive cell, whenever the light falls on the photoconductive cell, it is going to produce. Okay, this is the concept of photoconductive cell. Whenever the light falls, so we can have a photoconductive cell diagram as of like this. Okay, so resistance is going to be gets varied whenever the light signal is passing on this one. So this we can represent as light signals. Okay, resistor is variable. So whenever you are representing these lines, these arrows, it stands for photo input. Nothing but solar, nothing but sun rises or sun rays, or light energy, whatever it may be. Even from the light, normal light or visible light also we can get this. So this we can use as a LDR, light detector resistor. LDR, light detector resistor. It detects the lights and it will change the resistance value. So their characteristics will be like this. So as light falls, illumination gets increased. More light is falling on the photoconductive cell, then automatically the amount of resistance will decrease. So that conductivity will get increased. The same concept. Then the photovoltaic cell is the last topic of this chapter. So whenever the light falls on the photovoltaic panel, okay, so there is a glass cover will be there, a transparent adhesive, nothing but just like a gum type of material will be there. Anti-reflecting coating. Anti-reflecting coating is used that whenever the light falls, it should not reflect from there. Okay, so the falling of that light should be absorbed, should be extracted, or should be collected for the N type of material. So the N type of material is going to be collect the entire light rays falling on the solar panel, right? So that anti-reflecting coating is going to be gets placed, and there is a what you can have a depletion layer will be there, and p-type semiconductor material will be there. So whenever the light falls on this one, then there is a electrons are moving from p layer to n layer. So it is connected with the load, so that the flow of electrons will take place. So as the flow of electrons are nothing but the current that can be absorbed, we can connect directly to the load, or we can connect to the batteries to charge. Okay, simple example is in your calculator, you can see a black color, a small in size a photovoltaic cell. Okay, so through during this day operation, you need not to use the battery of what you can say calculator. During night time only you can use. Even for that daylight, I mean even light falls on this, it will charge. Okay, during in the completely closed or dark area only, then only the battery is going to be gets performed. So this is the animation what we can have whenever the light falls on n type of semiconductor layer, then automatically the electrons passing through from p type layer to n type layer, and it is gone circulating through the load. And then the photo junction devices, where we can have photodiode and phototransistor. These are the characteristics. So normal diode symbol, normal transistor symbol will be there, and only the change is here the light symbol. So this should be placed. Then only we can call it as a photodiode or phototransistor. Okay, so the photodiode and phototransistor will also works in reverse bias direction. Photodiode will works in reverse bias direction also. That is the advantage what we can have. So their operating ranges, their type of materials, these are all the things. Okay, so I will provide you the okay, right here. These are the reverse current directions. These are the forward characteristics and reverse characteristics also we can see, right? So these are all the things what we can use in various applications. Photoconductors, coupled devices, photomultipliers tools we can use, where we can have switching controls, digital signal processing. In these areas we can use. Even the CD, in order to get the whenever the light is falling on the disk, it is going to extract the data from the storage. Then sensing devices they will use in the LEDs, where technologies we can use wherever the light beams are required. There also we can use. There are various applications are there. Anyhow, that I will circulate these through the notes. So this is the symbol of a photodiode. See, so there is a small photovoltaic panel, just like that. The panel will be there. Whenever the light falls on this one, it starts conducting. So practical diagrams where we can have photo diodes. Okay, this is about the concept of